This is lecture 12 of physics 210A. Thermal physics, and we have been discussing thermodynamic potentials. We will continue with that in this lecture. So, just to recall, we have looked at the internal energy U, and U as a function of S and V gives du from the first law T ds minus P dV, or I should say from the central equation, and this is also equal to partial U with respect to partial V or partial S at constant V times ds plus partial U over partial V at constant S dV, and this gave partial U partial S at constant V equal to the temperature, and partial U over partial V at constant S to be equal to minus the pressure. And this also led to Maxwell relation. Similarly, we define the enthalpy, which is another thermodynamic function or potential, where H was defined as U plus pressure times the volume, and dH then came out to be T ds plus V dP. So, H is a function of S and P. I can also write this then as equal to dH ds at constant pressure times ds plus dH dP at constant entropy dP, and that gave dH ds at constant pressure to be equal to T and dH dP at constant entropy to be equal to P, and led to another Maxwell relation. So, notice that in U and in H, we have described processes whereby the variables are the entropy and the volume for the internal energy case, and the entropy and the pressure for the enthalpy case. And these processes become useful while describing constant volume or isochoric process in the case of internal energy, and isobaric process in the case of enthalpy. What about if something else is a constant? Suppose temperature is a constant, volume is a constant, what happens then? In that case, we define another thermodynamic potential, and that's going to be the topic of discussion in this lecture. So, here we are going to discuss another thermodynamic potential known as the Helmholtz function, or also Helmholtz free energy. And you will see not only it describes the thermodynamic processes for certain properties remaining constant, it also has connection with equilibrium and with the maximum work that a system can do. So, we will discuss all that in this lecture. So, we define the Helmholtz free energy F. It is also written as A in some books as U minus Ts, and this implies that the differential dF is equal to du minus dt times s minus t ds, and du can be written as t ds minus p dv minus s dt minus t ds is anyway there. So, t ds cancels and we get df is equal to minus p dv minus s dt. So, Helmholtz free energy F can be thought of as a function of v and t, and df, which is an exact or perfect differential, is equal to minus p dv minus s dt. This is also equal to partial of f with respect to partial v at constant temperature dv plus partial derivative of f with respect to t at constant volume dt. And again, I remind you, this is an exact or a perfect differential. And therefore, from this I can derive another Maxwell relation. Now, from this we get partial f partial v at constant temperature is equal to minus p, and partial f partial t at constant volume is equal to minus s. And since this is an exact differential, this leads to the Maxwell relationship partial p with respect to partial v at constant partial v p with respect to partial t at constant v will be equal to partial s with respect to partial v at constant t. This is a Maxwell relation. So, let me just repeat this in the next slide. We have taken a thermodynamic function f, which is u minus ts, and from this we have obtained that the differential, exact differential df is equal to minus p dv minus s dt, and equating this to partial f partial v at constant t dv plus partial f partial t at constant volume dt, we get partial f over partial v at constant t equals minus p, and partial f with respect to t at constant volume is equal to minus s. And this gives the corresponding Maxwell relation, taking the second derivative of f, which gives me partial p. So, I am taking the first derivative df by dv and then taking its partial derivative with respect to t at constant v is equal to partial s over partial v at constant t. That is the Maxwell relation. So, you can see from these equations that Helmholtz function is going to be useful describing processes that are isochoric, that is V equals constant, and isothermal, that is T equals constant. And we'll do that. But before that, let's use the Maxwell relation derived to show two things. So first, I'm going to use the Maxwell relation obtained here to get two important results. So let's do that. What is the Maxwell relation that we obtain from F? It says that dP by dt at constant V is equal to ds dt at constant ds dV at constant t. So first I'm going to use this to show that for an ideal gas, the internal energy depends only on temperature. So to show this, if I can show that partial derivative of u with respect to V at constant temperature is 0, then we have proved it. Now recall from lectures in first week that I had said that u is a function of t only. So recall from lectures in first week that I had said for an ideal gas, u is a function of t only. And also, we had said that Dittman-Zemansky says that for an ideal gas, PV equals nRT and u does not depend on P. So we are now going to prove this. That time I had deferred the discussion. Now we are going to prove this using Maxwell relation and the equation of state. So here we prove this using the equation of state for the ideal gas and the Maxwell relation. Obtained above. So let's do that. So if I take u as a function of V and t, then du is, u as a function of t and s. I know du is t ds minus p dv, and therefore partial derivative of u with respect to V at a fixed temperature T is going to be equal to T partial derivative of T with S with respect to V at fixed temperature T minus P. Now I am going to use the Maxwell relation and write ds by dV at T is equal to dP by dt at V, and therefore, partial u with respect to partial V at constant temperature is equal to T dP dt at constant volume minus P. Now, the equation of state for an ideal gas is P V equals nRT. I can write P equals n RT over V, and therefore, partial P with respect to T at constant volume is going to be nR over V, and therefore, du dV at constant temperature is equal to T times nR over V minus P. This part is P again, so this is 0. So, what we have shown using the equation of state for an ideal gas and the Maxwell relations that, or one of the Maxwell relation, that for an ideal gas the change in U, if I change its volume keeping T constant, is 0, and this implies U does not depend on the volume of the ideal gas, or U depends only on the temperature. So, if I consider U as a function of V and T, it will be equal to U of T only. Using the same, extending it further, using the same argument, I can also show that if I write U as a function of P and T, this will also be equal to U and T. Why? Because if I take U, P and T, I can write this as U, V and T using the equation of state. And U V T is U T alone. So, U does not depend on P also, because if it did, then the dependence on V will also come. In the lecture on another thermodynamic potential called Gibbs free energy, we will prove this explicitly, because I'll get a Maxwell relation there relating the pressure partial derivative. So, that's one result based on the Maxwell relation. The second result I am going to obtain is Stefan-Boltzmann law for black body radiation. So, let me just recall first what black body radiation is, or Stefan-Boltzmann law is all about. If I take a black body, that is a cavity where the radiation is trapped, and let it come out from a hole, then the intensity of radiation is proportional to T raised to 4. And you can also show that this intensity is equal to the energy density inside, which depends only on T, c by 4, where c is the speed of light. Now, experimentally, Stefan established that I is proportional to T raised to 4, and therefore, this implies ut is also proportional to T raised to 4, or ut is some constant times T raised to 4. So, this is known as the Stefan-Boltzmann law. Now, where does the name Boltzmann come in from? That comes because now I am going to derive it theoretically using thermodynamics. So, this is experimental fact. Now, theoretical derivation of ut proportional to T raised to 4 using thermodynamics. So, for this, I need you to know the following two things. Suppose I have this cavity and this is radiation going in here, which is known as diffused radiation. This is diffused radiation because it's going all over the place. There is no plane wave kind of thing. It's diffused. In this case, the radiation also gives pressure on the walls. So, if this has intensity ut, then the pressure P due to this radiation is also a function of T only, and it is U by 3. And this is known that the internal energy or the pressure depends only on temperature. So, that is known. It does not depend on the volume, only on temperature. So, we are now going to use this fact. Now, use du equals T ds minus P dV and write partial u with respect to partial v at constant temperature is equal to T partial S partial V at constant temperature minus P. So, this is exactly what we are doing in the case of ideal gas. Now, we are applying this to the black body radiation. So, here is this black body inside which there is this diffused radiation, and it has the total internal energy, which depends only on T, is equal to V times the energy density, and the pressure due to radiation is U by 3. And we have written that partial U partial V at constant temperature is equal to T partial S partial V at constant temperature minus P. Now, use the Maxwell relation partial S over partial V at constant T is equal to partial P over partial T at constant V. And then we get d by dV of u v at constant temperature is equal to T dP dt at constant V minus P. Since the small u depends only on the temperature, on the left hand side I get u, which is equal to T, and for P I use u by 3. So, this gets T by 3 du dt at constant volume. So, given a volume, that is what I get, minus u by 3. And this gives you T du by dt at constant volume is equal to 4u. And that immediately implies that u t is proportional to t raised to 4. So, experimentally, Stefan establishes that u is proportional to t raised to 4. You know all this law you have been using in your 12th grade. Sigma t raised to 4 is the intensity, and theoretically, it's Boltzmann who gives this law on the basis of thermodynamics. So, this is known as Stefan-Boltzmann law, that intensity is sigma t raised to 4. So, I have given you an application of the Maxwell relation. Now, let us discuss further significance of Helmholtz free energy. So, we have done the Maxwell relations through whatever we obtained through the Helmholtz free energy. Now, we want to discuss its further significance. So, for this, right now, we will consider systems that are in touch with a reservoir. It is a heat reservoir at temperature T. So, first what we want to show is that if the system is in a non-equilibrium state and goes towards equilibrium, then delta F is less than or equal to 0. You may say, if there is a non-equilibrium state, why is it that we are thinking that it can have a state function like f? So, what we can say is, suppose there is a system which is in non-equilibrium state. I can divide this into small systems, considering each one to be in equilibrium, and then write f equals summation delta f over each. And considering that the gradient of whatever properties are inside, they are not strong enough, so that they do not contribute, the gradients do not contribute to the free energy. Only the value of those properties V or T or whatever in these small sections gives the free energy. So, that is how one can think of this. So, if a system is changing spontaneously, it is going towards equilibrium, this is what happens. Let us show this. And this I point out now, and I will keep pointing it out. This is a result of entropy increase of the universe. So, the system, the universe we are considering is, here is this heat reservoir, and inside there is some system. And the two can exchange heat. So, we will now consider take the system to be at constant volume. It is under these conditions that the delta F will be less than or equal to 0. If the volume of the system is constant, then that's number 1. 2, Q given by the reservoir to the system will be equal to the internal energy change delta U of the system. And third, delta S will be equal to delta S reservoir plus delta S system. Since heat is being given away by the reservoir, this is going to be minus Q, and reservoir is at fixed temperature T plus delta S. Now, I am dropping the system, and this should be greater than or equal to 0. So, what do we have? We have minus Q plus T delta S is greater than or equal to 0. Now, Q is equal to delta U system. And therefore, I can write this again, dropping the term system delta U plus T delta S is greater than or equal to 0, or delta U minus T delta S is less than or equal to 0. And this is from the entropy increase of the universe, nothing else. And this is expressed, delta S is expressed in terms of the system properties. That's all we are doing. Although we are writing this in terms of system properties, you have to keep in mind that what we are finally doing is that the entropy of the universe is being taken to be increasing, and that is the sum of the entropy change of the reservoir plus the entropy change of the system. So, now since T is fixed, this gives you delta U minus T delta S equals delta of U minus Ts should be less than or equal to 0, and this is nothing but this implies delta F is less than or equal to 0. Now, remark. Since V is fixed, that's why we took Q to be equal to minus delta or plus delta U, and T at the endpoints of the process is fixed, delta f less than or equal to 0 is independent of the process in going from one state to the other. What it means is that since f is a state function and it is being evaluated at v and t at the end of two processes. So, that is what it is, delta f will tend to lower value. Now, as equilibrium is reached, then system does not change any longer and delta f will be 0 or f attains its minimum value. So, we can conclude as a system undergoes a spontaneous process or change at constant volume and is in contact with a heat reservoir at temperature T and at equilibrium, as it attains equilibrium, F takes its minimum value. Now, notice how we calculated F. The delta F was calculated as delta U minus T. Delta S, which is delta U minus T, not Ts, T delta S. The T at the beginning and at the end of the process is the same. In between, there could be changes, but right at the beginning and at the end, T is the same. This will be very important when we discuss the next significance of the Helmholtz free energy, and that is that it gives you the maximum possible work that a system can do. Now, here, before we do that, I want to discuss an interpretation pointing out a wrong one and the correct one. When you look at delta F equals delta U minus T delta S is less than or equal to 0, then as a system goes towards equilibrium, then an interpretation may be given that in approaching equilibrium, the system lowers its internal energy U, so that delta U is less than 0, and increases its entropy, so that delta S is greater than 0 and minus T delta S is less than 0. But this is not correct. This is not correct because delta U is coming from the heat given by the reservoir to the system, and we are writing that in terms of the change of the internal energy of the system. The only thing that is driving the system towards equilibrium is the maximization of the entropy. S max drives system towards equilibrium. So keep this in mind, and we can discuss it further in our tutorial. Now, second significance of Helmholtz free energy is what is the maximum possible work done by a system at constant temperature. So I have this system which is in contact with the reservoir, and we want to see how much maximum work can it do. So again, by entropy maximization, here is the reservoir, here is the system, this is at temperature T, and this is giving heat Q to T. Then I have the delta S universe to be equal to minus Q over T plus delta S system, and this should be greater than or equal to 0. So minus Q plus T delta S is greater than or equal to 0. Now the system does work. It could be doing it by expansion of the volume, it could be doing something else, it could be producing energy. There could be a battery, or there could be something else. Then I know by first law that Q, the heat going into the system, is equal to change in its internal energy plus work done by the system. And therefore, I have minus delta U minus delta W plus T delta S greater than or equal to 0, or minus delta U plus T delta S is greater than or equal to delta W. And since T is the same at the beginning and at the end of the process, so system could be doing anything, but it is in contact with a reservoir at constant temperature, so it does some work. and at the beginning and at the end temperature is the same, then I can write the left hand side as minus delta U minus Ts, and this is greater than or equal to delta W. And this is nothing but minus delta F, and this is greater than or equal to delta W. So if the system is going from, say, state 1 to state 2, then I can write that F1 minus F2 is greater than or equal to W. So maximum work that can be obtained is the change in the internal energy of the system. Now, this is slightly different from the mechanical systems. So in purely mechanical systems, the work done will be equal to delta U. So work done will be given by the change in the internal energy of the system. Well, but what we have now is that U1 minus U2 plus T S1 minus S2 is greater than or equal to W. Let's see if it is consistent. I have F, which is T U minus Ts. So F1 minus F2 will be equal to U1 minus U2 minus T S1 minus S2. So this is minus. Now, what is happening is, since there is heat exchange with the reservoir, that also contributes to the work done by the system. So suppose S1 is greater than S2. This will imply some heat has gone to the reservoir, and that means the work done will be less than U1 minus U2. And if S1 is less than S2, this will imply some heat has entered the system from the reservoir, and that will contribute to more work. So it's the thermodynamic system also takes care of, the entropy change takes care of that heat exchange also. So it's the energy difference plus the heat that it is getting or giving to reservoir that limits or that determines the work done by the system. So with this, let me now conclude this lecture saying that 1, a new thermodynamic potential, namely the Helmholtz function or Helmholtz free energy reduced. To using the corresponding Maxwell relation, we have shown that for an ideal gas, U T V is only U T, and also obtained Stefan-Boltzmann law. For black body radiation. Then we showed that at equilibrium, F attains its minimum value, and finally delta F gives the maximum work done by a system when its temperature at the beginning and end of the process are the same. Now, the third point, which is written in green, at equilibrium F attains its minimum value when the system is at constant volume and in touch with a heat reservoir. It should be not in touch, in contact. So, we defined a new thermodynamic potential, Helmholtz function, use the corresponding Maxwell relations to show that the internal energy of an ideal gas depends only on its temperature. At equilibrium, F attains its minimum value. So, when the system is approaching equilibrium, F becomes smaller and smaller and attains its minimum value when the system is at, so the system being considered as constant volume and in touch with the heat reservoir at temperature T, then F attains its minimum value. And delta F between two states gives the maximum work done by a system when its temperature at the beginning and the end of the process are the same. Thank you.